Good morning, AOBI. This is Mr. Dunning. Stand by. I have a math lesson for you. Yesterday, we talked about arc length, the circumference of a circle, angles, and the relation between angles and arc length. Let's review. Around a point, 360 degrees. On one side of a line, 180 degrees. Obviously, on the other side, there's another 180 degrees. The kind of angles that we're talking about are central angles. So the angle is equal to the arc. That tells us that there's 360 degrees of arc as well as 360 degrees of angle. This angle and that arc have exactly the same size. In example 1, we've made this angle 45. That tells us this arc is also 45. Over here on this side, we need to compare 45 to 360. And for this example, we're going to stay in degrees. 45 degrees compared to 360. 1/8. In other words, there's 8 of these in 360 degrees. Over here on this side, we have arc. There's 45 degrees of arc compared to 360 in the whole circle. That tells us we have exactly the same ratio. So whether we use angles compared to 360 or whether we use arcs compared to 360, we come up with the same ratio. Now the question that we answered yesterday is this number is 1/8 of what? Well, it's 1/8 of the circle. And so we needed a way to find how big the whole circle was. And yesterday, we concluded that the circumference of the circle is 2 pi times the radius. So, in this example, we want 1/8 of that. Listen to yourself speak. 1/8 of 2 pi r. 1/8 of 2 pi r. That's 1/4 of pi times r. If we knew the radius of the circle or the diameter, because you see a diameter is just 2 radiuses. If we make the radius 16, Then where there's an R in our formula, we can put that 16. Here's an important idea. You notice I didn't try to reduce anything right away, because here I see the 4 goes into itself once and into the 16 4 times. So my final answer here, this piece is 4 pi long. Come say hi to the students.
I don't want
No, come on.
it. Okay.
We have a guest, and I thought you'd like to say hi to Chris.
Hello. We're trying to keep our distance, but it's great to see you all. Have a wonderful rest of your show. Sorry for the interruption.
You're no problem, Chris. In example 2, we're only going to give you the arc. Not a problem. Here's how it goes. 60 compared to 360 is 1/6. This arc here is 1/6 of the whole circumference. And again, if we only knew this radius, we could solve this. So let's put in a radius. There. Now, what we want is 1/6 of 2 pi times the radius. 1/6 of 2 pi times the radius. And this points out why I want for you to just write numbers out like this before you multiply them, to see if you can do some reducing. And here, guess what? In this example, the 6 goes into the 12 twice, and that gives us 4 pi. So the length here the length of this arc is 4 pi. So whether we begin with an angle or whether we begin with an arc, it doesn't matter. If we begin with an arc, we compare that to 360. If we begin with an angle, we compare that to 360. Here's a check. If the arc is 60, the angle is 60, and we get exactly the same 1/6. So whether we use angles or whether we use arcs, we're still getting a fraction, a simple fraction. And that fraction is a multiplier. In this case, 1/6 of 2 pi times the radius, and in this drawing, the radius is 12. In this example, we have a circle, radius 15, and a 30-degree arc. We want to know how long that arc is. So we need to find out how big a piece of the circle it is. This arc is 1/12 of the circle. The circumference is 2 pi times 15. So, what we want is 1/12 of 2 pi times 15. Now stand by here, watch. I left the numbers strung out so you could see this. 2 goes into itself once and into 12 6 times. 3 goes into 6 twice and into 15 5 times. When we get done reducing, we end up with 5 halves pi. In other words, in this circle, this 30-degree arc has a length of 5 halves times pi. Remember, arcs and central angles are the same size. We compare central angles to 360, we compare arcs to 360. That will always give us a fraction, and that fraction is a fraction of the circumference. So in this example, we had 1/12 of the circumference, 2 pi times the radius of 15. Okay, in example 4, we have a picture here, and we're supposed to find the circumference of this circle. And you're saying, well, wait a minute, we don't have a circumference here. We've got a rectangle inscribed in the circle, but that doesn't give us a circumference. Yes, it does. If you know your Pythagorean triples, this triple is an 8, 15, 17 triple. And so we have a diameter. The circumference is going to be pi times 2 radiuses, or 1 diameter, and in this circle that will be 17 pi. So this is a mix of knowing your Pythagorean triples and being able to use that information to find the circumference. Let's do a review of the common Pythagorean triples. These are the triples that you're likely to see in many cases. 1, 1, square root of 2. This triple comes to us by dividing a square in half with a diagonal and using Pythagoras. 1 squared plus 1 squared is this piece squared. So this piece is the square root of 2. That's this triple here. But there could be multipliers involved. In a baseball field, for example, the length from home plate to first base is 90 feet. Well, they call this a diamond, but it's really a square on end, and all the base lengths are 90 feet. So we've taken this very drawing here, this drawing, and used a multiplier over here of 90. That gives us 90, 90, and 90 times the square root of 2. That's our first Pythagorean triple. The second Pythagorean triple, 1 square root of 3, 2, comes to us from an equilateral triangle. That we cut in half like that. That gives us a 30, 60, 90 triangle. If all the pieces here were 2 to begin with, then each piece here is 1. Again, using Pythagoras. One squared plus this piece squared is 2 squared. When we solve that triangle using Pythagoras, what we find is this piece here, square root of 3. That Pythagorean triple appears in many, many places, usually with a multiplier. So 2 times the square root of 3, and 4 would be this same triple. The other Pythagorean triples are these: 3, 4, 5, and multiple: 6, 8, 10, 9, 12, 15, 5, 12, 13, 8, 15, 17, and 7, 24, 25. It would be very wise to memorize these triples. It would be very wise to memorize these because you'll see them again and again and again. In example 5, we're going to look at something a little bit different than we have in the past. Let's look at a triangle here. Now these two pieces are radii of the same circle. Boys and girls, that means these two pieces are equal. That means this is an isosceles triangle. So the base angles are equal. Got that? This picture in example 5 asks for you to recognize this arc is equal to the central angle. So the central angle is 80. And in this picture, you need to realize that these are equal because that's an isosceles triangle. So both of these angles are equal. The angles sum in a triangle to 180. These two angles here are equal, and each one is going to be 50. That's using what we know about arcs and angles to solve for an angle inside a triangle. Tomorrow, we'll begin our discussion of area. Our discussion of area will include triangles, quadrilaterals, and circles. So tomorrow, when we meet, we're going to look at area of triangles, area of quadrilaterals, and area of circles. This is new, and we're going to show you why the formula is what it is. Once again, you've been a great audience. Hope you have a fantastic day. We'll see you tomorrow.